Today I want to talk about rates of radioactive decay and how we can calculate how much of a radioactive sample is left after a certain amount of time has passed. Um, when we do measurements in chemistry, there are a variety of different measurements. These are some of them. I am not going to read through all of these because it won't increase your understanding any, but I will say that um, in the past, in industry, the REM has been the unit of choice for determining how much radioactive exposure an individual has had. But it's becoming more and more common now to use the sievert. So we may see that occasionally. And a sievert is equal to 100 REM. So there are conversion factors throughout here that will help us to go back and forth between these units. Now, when we talk about how long a radioactive sample stays around, remember it's decaying. And as it decays, it's turning into a different element. And we can determine how fast that's going to occur by something called the half-life. The half-life is the amount of time it takes for half of a radioactive sample to decay. So, for instance, it says a radioisotope has a half-life of 15 minutes. How much of a 40-gram sample will remain after 1 hour? Well, using some common sense is a good way to solve some of these simpler problems, especially when you see them on a multiple choice portion of the test, of the AP test, which you do not get to use a calculator for. So, if we have a half-life of 15 minutes, at t equals 0, we have a 40-gram sample, it says. Well, in 15 minutes, half of that will have decayed. So we'll be left with 20 grams of our original substance. Now, remember, we've still got other material there. It's just not this particular isotope anymore. It's changed into something else. After another 15 minutes, 30 minutes total have passed, and we're down to half of that, 10 grams. After another half-life, 15 minutes, which takes us up to 45 minutes that have elapsed. We have 5 grams left. And finally, after 1 hour, the equivalent of 60 minutes, we have 2.5 grams of our isotope left, and that would be the answer. So being able to determine how many half-lives have passed, 15 minutes to 1 hour, that's 4 half-lives, we can cut the sample in half 4 times, and we'll have the amount of that particular isotope remaining. Now, unfortunately, problems aren't always that straightforward and that easy to solve. And then we start needing to have some other equations that will help us. One of those equations is this one right here, the fact that half-life is equal to 0.693 over K. Now, K is the decay or rate constant, which is different for every isotope. I know that doesn't make the word constant sound like it's being used correctly, but it is constant for that element. So, for instance, in this first example, it says technetium-99 is used to form pictures of internal organs of the body, and it's often used to assess heart damage. The rate constant of technetium-90 is 1.16 times 10 to the minus first reciprocal hours. The decay or rate constant are in reciprocal units. So what is the half-life of this nuclide? So if we know that the half-life is equal to 0.693 over K, and we know that K is 1.16 times 10 to the minus first reciprocal hours, then when we calculate that, we end up with a value for half-life of 5.97 hours. Since that reciprocal unit's on the bottom, it moves up to the top as, again, hours. So that's how you would use that type of calculation. Now, also keep in mind, and we'll need to use this sometimes, that you can find the decay constant if you need it by simply taking 0.693 divided by the half-life. And there are going to be times in calculations that we're going to be needing to use that particular equation. So 2 other equations that are of importance. The first one is that the activity of the sample is equal to the rate constant or decay constant of the substance times N. Um, if it's in this first equation, it's the number of atoms present, okay? So in equation 1, it's the number of atoms that are present. And again, activity is in disintegrations per unit time. A0 is at time 0, what are the disintegrations? So those are the values that we're looking at. The K constant again is K, time elapsed is T. This equation right here, ln of A over A0 equals negative KT is very important. Also, ln of N over N0 equals negative KT is important as well. They're essentially the same question. One of them is dealing with activity, radioactivity, the other with the mass or molar concentrations of the sample. But regardless, it honestly doesn't really matter which one you use. It's just kind of semantics. But you should use the A one for activity, the N one if you're dealing with numbers of particles, moles, etc. So one thing that will really help you out, this is a decay situation. So the bottom number, both equations, that bottom number is always the biggest. If you've got a bigger number on top and a smaller number on bottom, you've done something wrong, because you're always going to end up with, as time elapses, as time passes, you're going to get a smaller and smaller amount of that material remaining. Okay, so let's look at an example. It says the cobalt treatment used in medicine to arrest certain types of cancer relies on the ability of gamma rays to destroy cancerous tissues. Cobalt-60 decays with the emission of beta particles and gamma rays and has a half-life of 5.27 years. What would be the activity of a 1 gram sample? We're looking for activity of a 1 gram sample in disintegrations per second. So it looks like what we're actually looking for is A equals Kn. We're looking for activity. So we're going to use that first equation. So we need to know two values to get that activity. We need to know the decay constant, and we need to know the number of atoms present in this first equation for N. So to find K, remember that K is equal to 0.693 over the half-life. And it told us in this problem that the half-life was 5.27 years. So it looks like K is going to be 0.1315 reciprocal years. Now, as far as N is concerned, solving for N, what do we know about the number of particles? It doesn't tell us the number of particles. All it really tells us is that we're dealing with 1 gram of the material. So 1 gram of this sample, and this is cobalt-60. So as we work that to find the number of atoms present, we know that there's, for every 1 mole of cobalt-60, there are, and don't look up cobalt because it's not asking for just run-of-the-mill cobalt, it's asking for specifically cobalt-60, so 60 grams per 1 mole of the cobalt. And we know that once we get it to moles, that there's 6.02 times 10 to the 23rd atoms of cobalt for every mole. So we end up with 1.00 times 10 to the 22nd atoms. So we now have the values we need to plug into the equation. So let's go back and do that. We said that A was equal to Kn, so A is equal to the K value, which we just said was 0.1315 reciprocal years, times N, 1.00 times 10 to the 22nd atoms, which is going to give us a value when we calculate it of 1.315 times 10 to the 21st atoms per year. Now that is the equivalent of disintegrations per year, atoms that disintegrate per year. But what did the problem ask us for? It asked us for disintegrations per second. So now it's just kind of a simple conversion problem. We just simply need to change those years into seconds. So let's do that. 1.315 times 10 to the 21st atoms per year. And we know that for every 1 year, now this is important because we're talking about multiple years that have elapsed, 365.25 days, we've got to account for leap year. So don't forget that when you're dealing with this kind of equation. 1 day for every 24 hours, 1 hour for every 60 minutes, and 1 minute for every 60 seconds. So as we look here, we can see that our years have canceled, our days have canceled, our hours have canceled, and our minutes have canceled. And we're now left with 4.7 times 10 to the 13th atoms per second. And what that translates unit-wise is 4.7 times 10 to the 13th DPS, disintegrations per second. So that's the answer for that particular problem. Now, on the next one, it asks how much of a 3.42 microgram sample of cobalt-60 remains after 30 years. So we go back to the equation as soon as it gives us a time elapsed. This is very important. As soon as it gives us a time elapsed, we know we're using this equation. And we're dealing with a microgram sample, so we're going to specifically use ln of n over n0 equals negative kT. So the first thing that we want to do then is plugging in our values. We know that we've got ln of, and we're trying to find the resulting amount of the substance. So we're finding N0, it says, was 3.42 micrograms to begin with. We've already found K up above. Our decay constant for cobalt-60, we already said was 0.1315 reciprocal years. And it said we're wanting to know what happens after 30 years. So our time is 30 years. Now be careful if these don't match reciprocal years to years or reciprocal days to days, etc., then we're going to have to make sure and convert that time to the correct time. Okay, so what we have now is a situation where we need to get rid of ln. We need to get rid of that natural log. The way we get rid of natural log is to use e to the x. It was a unit or a process I believe that was created just to get rid of natural log in an equation. So we need to take e to the x of both sides. Now, most of the time in chemistry, what we do is we call it inverse ln. And if you look on your graphing calculator, if you have a graphing calculator, the second ln function is e to the x. And that's what you want to use. Okay? So we're going to take e to the x, inverse ln, it's often called, of both sides. What that does on this left side is get rid of natural log. So we end up on this side with n over 3.42 micrograms. And on the other side, just simply push second ln of this quantity of 0.1315 times 30. And if you do it correctly, practice it to make sure that you're plugging it in correctly. 0.01935 is what you should come up with, a positive value, which it should be positive. You can't have a negative mass. So now simply to solve for n, we need to multiply both sides by 3.42. We end up with 0.0662 micrograms of our isotope left at the end of 32 years.